give you the same value.
Yeah.
So you don't have to decay 5-hour decay down here and then divide it into that. You know what I'm saying? So you have 20 millicuries, and then we said there's 5 hours between, was it 8 a.m.? Okay, so you would have had, okay, here's 1 hour, 2 hours, 3 hours, 4 hours, 5 hours, and then if there's a half an hour, you multiply it times 0.944. Okay, you multiply all those together and you should get, 0.530. Because what would be the other way you would do that? Yeah, you could use the your activity. Basically, all you're going to be using is this part of the equation here, and you would have minus e the 0.1155 times 5.5 hours. I think they said 5.5 hours, right?
Mm-hmm. Yeah.
Okay, at 8 a.m. Okay. So if you take that 0.1155 times that, you should get 0.530.
0.63.
What you get? Maybe so 8, 9, 10, 11, 12, 1, so 5.5 hours. Is that what you got? And I've always, to me, here it is down here. So there's 1, 2, 3, 4, 5, and then the half an hour. So you should have gotten 0.530 with that. Oh, I put 841. I'm sorry, because it should be 891. And I'm going to send you the answer key to this, okay? Just make sure you don't share it with next year's class. Okay, let's take a look at number 23 here. Okay, on this one here, you're doing extrinsic uniformity every day with a cobalt source. And remember that camera sensitivity is counts per second per microcurie. Okay, but in this case here, they're just recording how long it takes to get 2 million or 3 million counts from their source. Okay, we normally expect it to increase because cobalt-57 decays. What's the half-life of cobalt-57?
270 days.
Okay, 270 days. Okay, so every day it's going to take a little bit longer. Okay, so what they're saying is, so you're doing all these daily tests, monitoring how long it's taking, and all of a sudden you get a day like this, where it's like 2.5 times longer. Okay, this is why you do this. Okay, so what would be the problem? Or which one of these things below would not be a problem? So an incorrect photo peak, so maybe you have it on technetium instead of cobalt. That would be a problem. Okay, if you have the wrong collimator, if you left the high energy collimator on instead of the low energy collimator. Okay, a cracked crystal or any kind of damage to your thing, or incorrect positioning of the point source. So if the point source is too far away, it's going to take longer. Okay, everything you do has to be reproducible. Okay. But why would an incorrect acquisition matrix not be considered a reason why this difference here? Now remember, what are the acquisition matrices?
64 by 64.
Yeah, you got 64 by 64. You might have by 8 or 64 by 64 by 16 or 128 by 128 by 8, 128 by 128 by 16. Okay. What do all of these different things mean here?
That's the window.
Pixel size?
Okay, basically, yeah, this kind of gives you a general idea of what the resolution is of the image, but it's also based on what they call your field of view. So, for example, if you have a camera that's 10 by 12 inches, which we don't have, but let's say that it was 12 inches by 10 inches, if that's your field of view, then to calculate what the resolution is, you would 10 by 12, and then you would divide that by the matrix. And that would tell you what the resolution is for that particular pixel. So in this case here, then the other thing that we have is, like you said, the depth. Okay, this tells you how many counts can be stored in each pixel. It gives you the color scale. So here you're able to have 2 to the 8th counts and 2 to the 8th colors. So 2 to the 8th is 2 times 2 times 2 times 2 times 2, or 256. Okay? This is also called byte mode. In computer terminology, anything that's 8 bits is considered a byte. And the reason why your memory and everything else is measured in bytes, can anyone tell me? When you buy a computer, it says that you have so many megabytes of RAM and so many terabytes of storage on the hard drive. Why do they use bytes?
As opposed to bits?
Or bits or anything else? All of the symbols, letters, spaces, anything on your computer has a code. Okay, they call it the American Standard Code for Information Interchange, the ASCII code. So the letter A might be 10110001. 1, 2, 3, 4, 5, 6, 0. This might be the code for the letter A. B might be 111100010. So every symbol on your keyboard, exclamation points, spaces, everything, has its own unique 8-bit code. So that's why they call it a byte. So if you have 1 megabyte of storage, that means you can type a letter 1,000,000 times before you fill up that space. Okay? Now, in computer imaging though, 256, if you're doing a static study of something, you may exceed 256 counts in that pixel. And if that happens, as soon as this thing gets to 200, it's 0 to 255. Okay? 256 would mean, 0 is counted as 1, so 0. There's 256 possible combinations that you have. So the problem is, if you're doing a static study, let's say you're doing a lung scan, and if there's a hot spot or something, you may actually exceed 255 counts in that pixel, which means as soon as that happens, this thing will reset itself back to 0. So you get a burned out spot there, you get a black spot with no counts in it. So in order to compensate that, we created what we call word mode. And basically, when a computer does a complete cycle of handling data, the word is the unit that they use for measuring how many processes can be taking place when the computer is actually analyzing data. So word mode, now for our nuclear medicine systems, we typically go with 16 bits, and that allows you 65,356 counts per pixel, or 65,356 different color scales. Okay. CT scanners are probably they're usually 512 by 512, and anywhere from 10 to 12 bits. Okay. But this is important because, like I said, it tells you how many colors you can display, and it brings out more subtle shades of gray type of a thing. But The bad side with this, can anybody see a downside to this? Okay, computer space, memory. In the day when computers first came out, memory was a premium. Those little 1.44 plastic discs that you don't see anymore, those things were probably about $5 a piece, and that probably even more than that. Okay, I mean now they're obsolete. The hard drives that we had were huge. They were 5 megabytes. They were like great big platters. We had a bunch of them. We could probably put maybe 10 to 12 studies on it, depending upon what the study was. We had rooms full of these discs. What we would basically do is recycle them. Those things were about maybe $200 a piece for 5 megabytes. Okay, so obviously now that computers are so cheap and more efficient, it's not a big deal. I mean, now I think you have several terabytes of storage. The problem now is you still have to archive though, right? So periodically you have to archive and clear out the space on the hard drive so that you can continue to acquire studies. So that's the big thing with this now is you have to stop, and sometimes the computer will tell you you don't have enough space for that study. Okay. So the problem, or the thing in the question that we're asking here though is the matrix size has no effect. I mean, if you're going for, if it's taking this much time, it doesn't matter whether I acquired it in a 64 by 64, 128 by 128, or 256 by 256. It's still going to take the same amount of time. Okay. And what else would you need to know about that? In the math book, it tells you how to calculate how much space a study would take up. So like if you're going for a renal study, okay, we typically use a 64 by 64 matrix whenever we're dealing with low counts. Anybody tell me why? Well, no. 64 by 64, it may be either 8 or 16 bits. But I use that for SPECT. I use it for dynamic studies. Okay. Why do I use a large matrix? I mean a small relatively sized matrix.
Makes it counts faster.
What?
Does it make it counts faster?
Well, remember going back to our statistics?
You can fit like more counts per pixel.
Well, you're looking at a larger area. So let's say that this is 64 by 64. If I go to 128 by 128, okay, let's say that I have 100 counts evenly distributed. Okay, I'm going to have 25 in here, 25 here, 25 here, 25 here. How many am I going to have in here?
10 or 12.
Well, let's say 100 divided by, let's make it 10. I'll make it an even 10, something. Okay, so I'd have 10 counts in each one of these, right? Possibly. If it was uniformly spread out. Okay, what problem am I creating here? Well, evenly distributed. What problem are we creating?
There's less counts in the area.
Yeah, so why would that be an issue?
Statistically, there can be more errors.
Ah, statistical error. So remember we said that statistical error is the square root of the number of counts divided by the number of counts. So in this case up here, the square root of 10 is about 3. So this is a 30% statistical error because there's not enough information. This other one up here, 25, the square root of 25 divided by 25, okay, that's a 5% error. That's still within our acceptable realm, isn't it? Okay. So whenever we do a SPECT study, are we getting a lot of counts when I do a SPECT study? That's right. I'm looking at it for maybe 25, 30 seconds at the most. So I may be getting 30,000 counts. Okay. So whenever I'm having low counts, I have to eliminate as much statistical unreliability as I can by using smaller matrix size. Okay. If I'm looking for resolution and I have a lot of counts, then I can use these larger matrices. Does that make sense? So that's why, you know, whenever we do a spec study, it's very rare that we use 128 by 128. Okay? You know, if you're doing a spec of a liver or something and there's a lot of stuff in there, then you can get away with it. Okay, let's take a look at the next one here. Radiation safety. The hands of a technologist who will be alluding to the generator should be monitored with.
The
Okay.
ring badge.
Yeah, remember the TLDs, and those are made out of what?
Lithium fluoride.
Okay, you need to know what these things are made out of. So it's lithium fluoride. The OSL is what we use for whole body because it's actually more efficient. Yeah, it works better. It's also more sensitive. This thing can detect 1 MR. Film badges can't detect anything below 10 MR. So I mean, if you had a film badge on and I process it, the film gets fogged simply because of the chemicals that I use to process it. So that's why I'm not able to see low levels of radiation. Okay. So anyway, so TLDs, and remember, what is the OSL made out of? Aluminum oxide. Okay, when doing a MAA scan, a patient has a right to left shunt. What should the technologist do? You have a lung scan, patient has a right to left shunt. What does that mean?
Means the MA is going to go into the systemic circulation,
Right. And why would that be a problem?
clog up kidneys, brain.
Okay, basically, instead of embolizing the lung like we do when we do a lung scan, we're going to be embolizing the brain, the kidneys, the heart. And normally if that happens, then you're going to get a stroke, heart attack, renal failure. So how many particles should we use?
That's the 100,000.
Under 100.
Yeah, about 100,000 or less. Okay. And remember, we use MAA. Now, we only use this for right to left shunts, or can we also use it for left to right shunts?
Just right to left.
Right, just right to left. Okay. You guys are good. You've got good memories on this, man. Very good. Over here, patients with known pulmonary hypertension or right to left shunt should be injected with as few particles, less than about 100,000, because the lung capacity is already compromised. So if the patient has pulmonary hypertension, you don't want to inject a lot of particles, because that's going to make the pulmonary hypertension worse. Remember, hypertension is where the blood can't leave the right side of the heart and get pumped into the lungs to get oxygenated. Okay? That's pulmonary hypertension. And if you inject more than 100,000 particles, you're going to be blocking more blood flow into the lungs. So that's going to cause the right heart to go into failure. Okay? Not a good thing, right? It says when all patients are injected in the supine position. Is that correct for lung scans?
Yes.
Right. Remember, why would we not inject them in a sitting position?
Because the particle going to be on a base.
Okay, right. Gravity's going to make it the lung bases. Okay. Patient. Now, how long? Now, normally you're supposed to inject the MAE over a period of a few seconds. Okay, because the breathing allows it to follow a more normal distribution. When patients are in an upright position, blah, blah, blah. Increasing the size of the particles is not recommended in any case. Okay? That's just, it says flushing the syringe with blood will increase the chances of clots. I don't know if you've ever seen, I think I showed you guys some pictures that had clots in them. And that's what happened. Somebody, you never allow the flash to go back into the syringe, okay, on MAA. You never injected plastic tubes either, as it gets stuck in the tubing. Okay. What is the preferred tracer for intermittent gastrointestinal bleeding? And that's right, red blood cells. Okay? What is the recommended radiopharmaceutical for acute GI bleeding? Sulfur colloid. Okay. So, and I know that every time you get a call, the nurse will say, "Oh, they're actively bleeding right now." Well, the thing is, I rarely have ever that happens. Yeah. So most of the time we use the red blood cells, and then we do the bleeding. How long do you guys go? Usually 2 hours.
2 hours.
And I normally bring them back in 24 hours.
Oh.
The other thing I do is remember to always take a picture of the neck area after you're done.
Is that free tech?
City free tech.
We're not going to ask about Schillings, right?
Now, the Schillings test, basically, or at least the last time that we reviewed the test, I mean, I was looking at it in 2009, I think. They removed all of the Schillings test questions, so there shouldn't be any there. But remember that this used to be a really popular test for pernicious anemia. Some people just cannot produce intrinsic factor, and so that means that vitamin B12 is not absorbed. As a result, the red blood cells don't mature. Okay, they're very, very small. They don't have any hemoglobin in them. So the problem then is that this is where you give radioactive B12, and then you may do it with intrinsic factor. And if it's still abnormal, then you get antibiotics for 5 days and repeat it. But don't worry about it. You don't have to do Schillings test anymore. The main thing is collecting urine for 48 hours. Okay, you give them a big thing to put their urine in. So the next one, based on the day's clinic, all of the following should be ordered except. Okay. This one you guys should be really familiar with. Okay. So we got a renal function study, so what's that going to be? Okay, the mertitide or DTPA, probably be mertitide. Okay, what about total body?
MDP.
MDP, HDP, methyls diverticulum,
Straight tech, protectate.
protectate, and then the hepatobiliary.
Mebuprofen.
Okay, so you see how that works? Be prepared for that type of question. Okay. Here you go. You got a package 2.8 curies, generator 3.5 MR at 1 meter, and 95 MR per hour at the surface. Which of the following labels is required? Okay. Well, obviously
Just the QE.
huh?
It says QE.
Yeah, it's a lot of activity. But remember the yellow 3 because which one of these is going to? Remember, if you remember what yellow 2 is, what's yellow 2?
Is it
50 on
under-
the surface
Yeah, it's more than 50, isn't
and
it?
10 at
And the thing that's important here is this, okay, because we got yellow 3. We could have yellow 3, but the transportation index is the key thing on that. Remember, the transportation index is the reading at 1 meter. Okay, so this is the important thing here, because I could have radioactive yellow 3 and the transportation index of 95, and it would still be wrong, wouldn't it? Okay. It says yellow labels are for 50 milligram at the surface. And this is 95, so that's the reason why here. Okay, because the reading it should be 10 MR at 1 meter, and that's okay. Okay. Is this helpful, by the way, or are you guys putting you all to sleep? Somewhat helpful. Nebulizer for which lung imaging radiopharmaceutical? Would it be better if I didn't have the answers here? Would that be more of a challenge for you? We can do that. Because I do want you